So when we want to do the dynamics of atmosphere and ocean, it's good to have a sense of what is so special about it. For example, you've probably done some fluid dynamics in uh, smaller scale systems, flow through pipes, maybe even some aerodynamics and so on. But Earth, few things become very critical. One, of course, is the energy, right? Energy is coming from the sun. The balance happens by the energy that's going out from the Earth. We'll look at those energy balances. But the energy distribution itself depends on one critical fact, and that is Earth is a sphere. Well, it's a bit squished because of centrifugal force and so on, but nonetheless, it's essentially a sphere, which we will see that results in more energy per unit area coming in at low latitudes than at high latitudes. And then that also results in more energy going out than coming in at high latitudes. So there is a net energy loss, and there is a net energy gain, more energy coming in than going out in the low latitudes. Obviously, to prevent the low latitudes from getting warmer and warmer because of excess energy, and the polar latitudes getting colder and colder because of net deficit of energy, energy is being moved constantly on the Earth. This is what gives us atmospheric circulation, and then the atmosphere drives the ocean. So ocean has two types of circulations, as we will see. But this nice map from a satellite shows many interesting features. There are swirly motions, there are these tilting flows as you go away from the tropics, and this is basically humidity, clouds. Okay, so atmospheric circulation moves everything that's in it. Clouds act as a tracer to some extent. They have a feedback as well. We will see what that means. So what sets up the scales and the various features that we see here? We can see this better in this animation of water vapor transport in the atmosphere. And you can see these nice swirly motions, large scale, small scale, and these angular transport across these mid latitudes. This is related to something that we already mentioned, something called baroclinic instability. So it turns out that if you try to move a parcel of air from the tropics to higher latitudes, it begins to go unstable because the angular momentum cannot be conserved anymore, which means there is an instability. So energy has to move from the tropics to high latitudes because there is this energy excess and energy deficit situation, and nature does not like gradients, right? So it tries to smooth it out. So it's a question of how the energy can be still moved north when there are these instabilities along the way. So some cute features show up. We won't get into the very details, but we'll touch upon it. Okay. The other thing that matters, I mentioned already stratification and rotation producing special effects when I was talking about the introduction to the course. Here is a scaling shown. Again, don't worry, we'll come back to the details. It's called Rossby number. It's got U over L, where U is a typical, let's say, horizontal wind speed, and L is the horizontal scale over which the winds change. So U over L gives you the 1 over time scale, typical time scale in the atmosphere. And tau rotation is the time scale of rotation of the Earth, which is 24 hours. So it turns out that anything that tries to move close to the rates of rotation or faster can begin to get affected by Earth's rotation. Okay, we are moving very slowly, so we don't feel the effect of Earth's rotation. We have evolved to live on this rotating framework, so we are happily going around. But if we try to fly like Superman at very fast speeds, technically we should feel the impact of rotation. Superman is Superman. He doesn't feel it, but nonetheless, This scale turns out to be important. So the book shows this nice experiment they do where they have a fluid with some dye inside, and then they perturb the dye on a rotating table. Why? Because if the table is not rotating, then the dye would slowly diffuse away. It's like putting milk in a coffee cup. The milk would just diffuse away. But if you put milk and put a spoon and swirl it, then you may end up creating swirls of coffee and milk with black and white forming these nice features, which is what is shown here. So it turns out that on a rotating system, if you have a stratified fluid or otherwise, there is a certain rigidity that can develop parallel to the axis of rotation. Okay, it's called Taylor column, which we will look at. That begins to produce these swirls. Okay, so even if you look at Hubble telescope and its images, you will see nebular dust, but you will also see these nice large swirly features because the universe is rotating. So rotating systems produce these special features, the rigidity parallel to the axis of rotation. So we will see what that does to some of the phenomenon in the atmospheric and ocean dynamics. So that's what makes the Earth fluid dynamics special. Rotation and energy gradient, and then there is stratification. So many scales evolve out of that, many special features evolve out of that. We will see those.